Hi, my name is Ali Lamadrid, and this is my video lab report for the Phys2212 Lab 5. So for this experiment, the objective was to observe the interaction between a falling bar magnet and a tube of aluminum foil, as well as the resulting induced current from the bar magnet. So to complete the experiment, I obtained observational data of the interactions between the magnet and the aluminum foil by recording the fall time of the bar magnet through the foil tube. And then I recreated this entire scenario within a computer simulation and compared the results of the two methods. So for this experiment, there were several principles that came into play. The first was Faraday's law, which states that in the presence of a time-varying magnetic field or current, there's an EMF with magnitude equal to the change in magnetic flux. So we used this principle to observe the flux and calculate the resulting EMF. Next was the Biot-Savart law, which is an equation that describes the magnetic field generated by a constant electric current. So this is the equation that we used to help find the magnetic force from the current. Newton's third law, which states for every action in nature there's an equal and opposite reaction. We used this when comparing the force on the loop from the magnet and the force on the magnet from the loop. And then Newton's second law, which states for an object with constant mass m, the force F is the product of the object's mass and acceleration. We use this to help calculate the gravitational force on the magnet. And then finally we use Lenz's law, which says that an induced electric current flows in a direction such that the current opposes the change that induced. So for this experiment, I completed 5 different trials of dropping a magnet through an aluminum foil tube, like you can see on the right. And I used a timer to record the amount of time it took to fall through the tube. And these are those results here on the right. And after completing 5 trials, I got that on average, the fall time for the bar magnet was 2.08 seconds. So here is my computational model recreating the physical experiment that I performed in the last slide. On the left, I included some of the important code that was used to model the system. You can see on the left at the top, I was calculating the magnetic flux, and then in the middle, steps 5 and 6 was used to calculate the B field at each individual ring that in the end we combined to represent the entire tube of aluminum foil. And then at the bottom, you can see calculating the force of the magnetic field on the magnet, and then also we calculated the gravitational force by doing mass times the gravitational constant. And then we combined those to create Fnet. And then finally, we updated the magnet's velocity and position using Newton's second law. So a couple questions for the experiment. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So if the resistivity of the conductor were reduced to 0, there would be nothing to prevent a large buildup of the current. This would result in a really high current that would increase the upward force on the magnet so much that it would eventually cause the magnet to come to a complete stop. And the current needs the moving magnet, or the current is induced from the moving magnet, but because of the lack of resistance, the current would be big enough to maintain itself without the movement of the magnet any longer. What if holes or slots were cut into the tube? How would this affect the ring currents in the model? So if slots were cut into the tube, they would limit the growth of the current. So the current would not be able to be as large as it is without any slots or holes. And this would in turn decrease the force acting on the magnet. And as a result, the magnet would fall faster through the tube than it would if there were no holes or slots. And then at the bottom is my glow script code. Thanks for watching.